everyone, I'm Professor McBain and welcome back to Chem 100 and welcome back to our series on nuclear power and nuclear war. This is part 2 in our lecture video series, and in this one we are going to be focusing on nuclear power plants and a couple of nuclear power plant disasters that have happened in recent years. Alright, welcome back. In our last video series, we had just finished talking about how to enrich uranium to the appropriate proportions that it can undergo fission very readily and be efficient at that fission process. And we had also just finished talking about how the very last gaseous diffusion plant, which helps you enrich that uranium, had just shut down in 2013 due to all sorts of leaks and contamination issues. So let's talk about nuclear power plants. So a power plant in general operates off of all of this stuff over here. So let's ignore the containment structure and let's just talk about all of this over here. So most traditional power plants operate on the basis of heating up liquid water and turning it into steam. And the higher and higher temperature that you can make the steam get to, the more and more pressure that steam will exert. And so that pressure is used to turn a turbine, which is attached to a generator. A generator is really a dynamo, but in general, the generator is what generates the electricity. So when the steam exerts all of that pressure, then eventually it cools down, and then that steam just gets to be recirculated and recirculated forever and ever until until you don't need it anymore for some reason. So in traditional power plants, we typically be heating up the water with, say, coal or diesel or gasoline or something like this, okay? So coal-fired power plants, they use coal over here to heat up the water into steam. So what makes a nuclear power plant special is that instead of coal or gasoline to heat up the water into steam, you just use this coolant, which is actually pretty darn hot, to heat up the water into steam. Okay, so how did that coolant get hot in the first place? Well, because you've got these fuel rods of uranium dioxide right here, okay? And if the uranium is exposed to more uranium dioxide, then they can share those neutrons that we were talking about in the last video to undergo their fission process. Let me hop over to that slide real quick. Right, so remember this reaction right here, you need uranium-235, but also some neutrons, which the uranium is almost always letting go of at some rate. And so if one of them collides with some uranium, then it will undergo that fission process, but it will also release even more neutrons so that more and more fission can continue to occur. So now you might notice that there's also these things called control rods. These control rods tend to be made of certain elements that can block the neutrons from getting to other uranium nuclei. For example, in Chernobyl, these control rods were made of boron, okay? And so if you block the neutrons from going to more nuclei of uranium, then you block the fission process, and then you basically are slowing the rate at which the reaction occurs. And so then if things aren't heating up nearly as much, then you won't generate as much steam, and so then you'll basically be slowing down how much electricity you're generating. On the other hand, if you raise up the control rods, then more surface area of the fuel rods will be exposed to each other. They'll undergo more and more fission, they'll release more heat, the primary coolant will get hotter, and then you'll be generating more steam and thereby generating even more electricity. Okay, so everything in here with the control rods is literally how you control the rate of electricity being generated. Now, you could technically just expose all of this directly to the water, right? And then you just cool it back down and so on and so forth. But you need this primary coolant to be contained away from your water source because this coolant is directly exposed to the uranium and the other potentially radioactive byproducts of the fission process. So it's actually much safer for this coolant to be shut off from your water source because that water source goes back to a body of water like a lake or an ocean or a creek or something. We don't want all of that nasty stuff getting into our body of water. In addition, the coolant might possibly be made of some other chemical that that doesn't heat up quite so quickly, or something like this, or maybe it heats up even more quickly than water might, and so you can get it to higher temperatures much more efficiently than you would have with water. Anyway, it's a good idea to keep the primary coolant physically separated from the water that that gets turned into steam. Okay. So there's a nuclear power plant in a nutshell. There are variations on all of this design here with the containment structure and the control rods and so on. Those of you that have seen HBO's Chernobyl, you might have had a hint about that, because there might have been a hint about these control rods being tipped with graphite as opposed to boron or something like this. We're not going to worry about that too much right here at this point in the semester, or possibly ever, but just know that there can be some variations that make this whole process more safe or less safe, or more efficient or less efficient. So, as you might imagine, there are advantages and disadvantages with using nuclear energy, but the main advantages are that you can get a large amount of power produced for a very small amount of that uranium fuel, which we talked about at the beginning of this lecture series in the last video. Let me go back to that real quick. All right, remember this slide, we saw firsthand that you can get 71 million kilojoules of energy per gram of uranium that you start with, whereas with gasoline, you can only get 48 kilojoules per gram of octane. So it's very efficient, which helps it be a green process. Another advantage is that there are no greenhouse gas emissions. So if we go back to this setup, you can see that, well, everything stays contained right here, all right? So yes, eventually the fuel rods are converting into other radioactive byproducts, but none of those are carbon dioxide, so that's good. And yes, you're generating steam, but eventually that steam condenses back down to water. And you might have seen in these cooling towers over here, yes, there's always like this stuff coming out of it. That's not smoke and it's not carbon dioxide, it's just water vapor. All right, so eventually that water vapor goes up into the clouds, and it might precipitate and just become rain clouds and fall back onto the earth. So that's good. So yeah, there's no generation of carbon dioxide along with this process, whereas with a coal-fired plant, diesel, or gasoline-fired power plant, carbon dioxide absolutely would be a byproduct of just turning that water into steam. Another advantage is that, well, coal mining is dangerous, right? And so you might say, well, uranium mining could be dangerous too. And while that's true, well, you only need to mine so much uranium to generate the same amount of energy that you would compared to how much coal you would have had to mine otherwise. Okay, so because there's less uranium that you have to mine, it doesn't pose as much of a hazard to the lives and livelihoods of the people doing the mining. So those are the main advantages of using nuclear energy. Some of the disadvantages, the main one is that whatever spent nuclear fuel you have, it's got to be stored, and it's got to be stored safely. And usually, even though a fuel rod might not have enough uranium-235 to undergo a reasonable amount of fission at one point, there's usually at least a couple of uranium nuclei that haven't undergone that fission. And so it still poses a threat to the safety of humans and other organisms like that. Not to mention all of the other radioactive isotopes that you're generating as a byproduct of the fission process. So what you do with these fuel rods is that you store them in these very, very thick lead and cement lined containers, so that whatever radioactive stuff they emit, it's all just contained and it doesn't affect any living organisms. But as you might imagine, the land required for that storage can get pretty pricey. And then, of course, the storage containers themselves are pricey. And if they're stored along a fault line, like anything in California or along the San Andreas Fault, then if they undergo an earthquake, then they might get cracked or something like this. The uranium hexafluoride also needs to be stored as well, and it's a bit of a hazard in addition to the other stuff. And then, of course, there are power plant accidents. And so those aren't very good by any means. So let's talk about 3 accidents that happened in the last 50 years. One power plant accident that actually happened on U.S. soil occurred in 1979 at 3 Mile Island in Pennsylvania. So there was an issue going on with the secondary coolant system, but also it had to do with the primary coolant. Okay, so the primary coolant valve was stuck open, but the open light was turned off because the open light was related to whether the solenoid that controls that valve was able to open or close. So the solenoid itself was malfunctioning, and so that light was off, and yet the valve itself was stuck open. So what does that mean for what's actually physically happening? It means that some crazy how this primary coolant stuff is really, really hot, and yet it's escaping. And so there's no primary coolant that's going through the water, and so then there's no electricity that's being generated because nothing in here is hot enough to generate that steam. But what was really going on was that there was tons of primary coolant that was being heated up, and it was just escaping over here before it ever reached the water that actually generates the electricity. So what the operators decided would be a good idea was to lift these control rods out further and further to make more fission happen. And so they were heating up these fuel rods a whole lot more, and they were gradually boiling off the primary coolant in hopes of generating more electricity without realizing that there was this valve over here that was stuck open. And so along the way, they also ignored other signs and alarms. There was also a thermostat somewhere in the primary coolant system that just kept on going up and up and up and up and up. And yet everybody was paying attention to that open light being off. And they're like, no, it's fine, it's fine. We just got to pull out the control rods. So eventually they kept boiling off that primary coolant so much that it just all boiled away. And so that's what you call a loss of coolant, right? Is because you literally boil away all of that primary coolant. Once you do that, then the fuel rods don't have anything to cool them back down and to keep them in a solid state. So they will just keep on reacting with each other until eventually they melt, and then they're no longer in this rod shape. If they're no longer in that rod shape, well, when you try to pull down the control rods to block them off from each other, the control rods will get stuck, and then they won't actually be able to block the fuel rods from each other. And then that's when you start to have a fuel source meltdown. Okay, so that's exactly what happened at 3 Mile Island. So while that happened, there was also a buildup of hydrogen due to a side reaction that just usually takes place in a containment structure. And so what the operators decided to do was they decided to vent that primary containment system in order to get rid of the hydrogen gas, because if hydrogen is mixed with very, very hot temperatures, well, eventually that hydrogen will explode, okay? And so rather than have an explosion along with their loss of coolant meltdown, right, which would then spread that uranium far and wide, they decided to vent that primary coolant system a little bit more and let go of that hydrogen gas, as well as the primary coolant that had been boiling off and which was mixed with all of those other fission byproducts. And so what happened as a result of this? Well, there weren't any alpha emitters that were in that primary coolant that got vented. And at the time, in the late 70s, it was thought that alpha emitting radioisotopes were the most dangerous ones for people to worry about. And so the NRC came through and they just made sure that there weren't any alpha emitters, and they told the public, oh, it's fine. And yet over the next 20 years or so, both humans and animals alike saw a lot of miscarriages and birth defects across the area. And there was also slightly higher incidence of cancer in people. So it's thought that even though there weren't alpha emitters, there might have been beta emitters, gamma emitters, and all of that were in the primary coolant, in the contaminated primary coolant that was vented. All right, so that's 3 Mile Island. Now, a very famous nuclear power plant disaster is Chernobyl. And you all who have seen HBO's Chernobyl, you probably know a few more details than I've got listed here. And all of those details certainly, they certainly take up 5 2-hour episodes, don't they? So here are all of the spoilers, but I still recommend that you go and watch that series. So there was a systems test that needed to be ran before Chernobyl was actually in operation that they just kind of bypassed. And so eventually, though, they needed to perform this systems test. Well, they did it under all of these conditions that actually weren't approved in the manual. And so because they kept on going off book, there was a big old power surge. And the director, as a result, the director instructed the operators to ignore the alarms and all of the automatic emergency systems that were about to go into place as a result of this power surge, because he wanted to get that systems test finished. And at the very last minute, there was absolutely a big power surge, and the only thing left to do was to slam the control rods down and block off the fuel rods from each other. But those of you who have seen Chernobyl, that was a big problem because those control rods were tipped with graphite, which actually makes the fission process spike very quickly. And so even though they hit basically the big shutdown button, it actually caused an even bigger surge, and that led to a big old explosion. The fuel rods fractured from the heat, and they blocked the rest of the emergency shutdown process, and then the fuel rods just heated up and up and up and up and up, and then boom. So this was actually a big explosion that happened, right? So there was that buildup of hydrogen that the 3 Mile Island folks were trying to avoid, and it made everything erupt, okay? And so then once that ruptured reaction vessel was exposed to air, then it caused even more ignition of the graphite itself. And so then the fire that resulted released radioactive smoke plumes for a whole week. And part of the big challenge was even getting the fire to be extinguished at all. And of course, that's part of the series as well. So we're starting to see a little bit of a theme here, right? So this guy ignored the alarms, the automatic emergency systems. These folks had a fundamental flaw in the design of those indicators and emergency shutdown protocol as well. Yeah, so again, we're kind of starting to see a theme here, right? It's like if there's a misunderstanding with what is a safe process, or if you're ignoring all of the emergency protocols in the first place, then you're gonna have a big explosion, right? Okay, so we've got 3 Mile Island, we've got Chernobyl. The most recent power plant disaster occurred in 2011 at Fukushima Daiichi in Japan. And everything was going very well, but then all of a sudden there was an earthquake, which happened in the middle of the Pacific Ocean, but then there was a tsunami, and that's really where the issue came. This power plant, I think it's 4 power plants or so at Fukushima in Japan, they had all been built along the coast because they were using ocean water as their water source for the steam generation process, right? And so that's all well and good until you have something like a tsunami that comes in and ruins a bunch of stuff, okay? So the emergency systems actually weren't able to function anyway because the tsunami that came in and actually killed all of the backup generators. And so because those systems were killed, they couldn't keep the cooling pressure release cycle from continuing, and so then they also had a loss of coolant meltdown and an explosion in 3 of their reactors, right? And so then there was also a big release of that primary coolant stuff, goop, directly into the Pacific Ocean, and that's not good, and we're still monitoring effects from that. There's still a lot of people that are pretty concerned with now obtaining fish from the Pacific Ocean because there's now a concern that they've been contaminated with all of the primary coolant that had been contaminated from, being part of a nuclear power plant. So again, we've got this theme with nuclear power plants. So the theme that we've got going is that folks who are operating these nuclear power plants need to go by the book. They also need to have fundamental understanding of the design of the reactions and the reactor itself from top to bottom. It's also a pretty bad idea to set up nuclear power plants either on ocean fronts or along fault lines, because if you have natural disasters like this occur near that power plant, then there's going to be nothing that you can do to stop things from going haywire. All right, so that concludes our section on nuclear power plants, and I'll see you next time for our discussion of nuclear weapons. Thanks for joining me.